Riding the wave of the future. And this is the contents I'm going to in my slides today. First, I'm going to explain what is RUSEF, why do we use ocean waves energy, the potential wave energy around the world, the types of waves, ocean waves converters, the energy and power of waves, the conceptual design, the manufacturing, site testing, conclusion, and I'll end up with the future works. Yep. So what is RUSEF? Basically, RUSEF is an ocean waves energy converter that's located in the shoreline. It's my innovation, and RUSEF stands for Renewable, Useful, Sustainable, Environmental Friendly Ocean Waves Energy Converters. It aims to produce a clean electricity at a very competitive rate. And the benefit of using RUSEF is it does not pose any threat to the marine life as well as the environment. And it has a very bright prospect. As we know, the government just announced $625 million allocation for the renewable energy in the recent budget. And this is my research question for RUSEF. Can we use ocean wave energy as an alternative energy source for the future? Well, let's look at it. The Australian population will reach by 42 million by 2050. And in the same time, the electricity prices has risen so much. So in order to provide affordable electricity as well as to supply to the rising population, that's why we have to find an alternative energy source for the future. So why do we use ocean wave energy? Well, as we know, the fossil fuels is going to be depleted in the next 20 years, so we should reduce our dependence on using fossil fuels. In fact, ocean wave energy is a free, renewable, and clean energy which can be used to be converted into clean electricity without any pollution. And the ocean wave energy converter has little visual and environmental impact. And the ocean wave is in abundance. It's available 24 hours a day, 365 days a year. And the estimated potential of using ocean wave is 5 terawatt worldwide. And the benefit of using ocean waves compared to other renewable resources, because it's easy to predict compared to solar or even wind. Yeah, I'm going to show you the potential wave energy around the world. These numbers indicate the average annual wave power levels as kilowatt per meter of wave run. As you can see in Australia, we are fortunate enough to be in Australia as we are surrounded by these high numbers, especially in Tasmania and Western Australia. So I'm going to explain the types of ocean waves converters that currently existing in this world. They are grouped based on their location. I'm going to start off with the onshore. And we have the oscillating water column. The compressed air, the incident waves will compress the air, and the compressed air will drive the whale's turbine. And the waves retreat due to the differential pressure. The air will come in from this side and will drive the whale's turbine to produce electricity. And there's another type of onshore, which is the taper channel. Due to the narrow channel, so the waves will increase in height, and because of the differential height here, it will drive the turbine to produce electricity. And for the nearshore, we have the overtopping device, which in this case, I use a wave dragger as my example. As you can see, when the waves hit the wall, and then it will climb on top of the wall, and because of the differential height here, it will drive the cup-like turbine and the generator to produce electricity. And we have the point observer, as you can see from the animation here, is make use of the heavy motion of the wave to produce the electricity. And for the offshore, we are categorized into three on how it operates. We have point observers, the terminators, and the attenuators. You can see the terminator is operating in parallel to the incident wave here, while the terminator is operating in perpendicular to the incident wave, and the point observer is just same like the before. Yeah, I'll show the example of terminator, in this case which is the wave roller. And for the attenuator, we have a famous case of Pelamis. And the point observer, just like the animation I showed to you before. Yep, so I'm going to explain the energy and power of waves. This picture shows the wave nomenclature that we use. And as in this picture, we can see that 95% of the ocean wave is within this step. So it's important that we have a device that can convert the energy from this step, And the velocity of the ocean waves is illustrated in the formulas over there based on their water depth, the deep water and the shallow water. The Vg is just the group velocity, which means the velocity of the energy propagation. And the energy density of an ocean wave is given by this formula, and the power of wave is just a product between the group velocity and the energy density of ocean wave. Before I start my conceptual design, I have to lay out my requirements and constraint. My requirement for the device is to produce 500 watts of electricity, and the constraints are because I'm still a student, so I have limited time and budget constraint. And the safety concern as well. That's why I have to place my device on shore. You can see this is the side view of my device, RUSEF. The float is the important part, and it's guided by the roller here. So when the incident waves hit the float, due to the buoyancy force, the float will move outward. And when the waves retreat due to the gravitational force, the float will move downward. And this up and down will drive the unidirectional gearbox, which in this case I use rack and pinion. So how rack and pinion works? As you can see, when the racks move outward, the pinion will rotate in this direction. When the racks move downward, the pinion will rotate in this direction. So if the alternator, which is used to produce electricity, is attached to the pinion here, imagine the alternator will be spinning clockwise and anti-clockwise. It will be very inefficient. This is why I came up with a solution. Basically, just make use of the sprocket that you can attach from the bicycle. It's free at one direction and it's engaged at the other direction. So you can see I'm just using two sprockets, but in different phase. So when the racks move outward, sprocket A will be engaged. It will drive the shaft and drive the gear A at the same time. And because sprocket B will be free, that's why it doesn't rotate the shaft. But because gear B is connected to gear A, that's why gear B will be driven by gear A. Whereas in this case, when the racks move outward, sprocket A will be free. It doesn't rotate the shaft over there, while sprocket B will be engaged and rotate the shaft and rotate gear B. And because gear A is connected to gear B, that's why gear A will be driven by gear B. So as you can see from these two pictures here, regardless of the direction movement of the rack, gear A and gear B will always rotate in the same direction. So I'm going to explain the torque gear ratio and the buoy volume. Assuming that the starting torque of the alternator at a given maximum load, we know that value, then we can work out the torque at the sprocket, because we know that the torque is a multiplication of gear ratio. That's why the torque at the sprocket is given by this formula. So once we get the torque at the sprocket, we can work out the force at the sprocket. And then the next thing that we have to know is the buoyancy force, which is given by rho Vg. Rho is the density of liquid, G acceleration due to gravity, and V is the volume of the buoy, which is attached to the rack here. And the weight of the rack can be measured. So in order to rotate the alternator, the buoyancy force has to be more than the weight of the rack and the force at the sprocket. By working out this relationship, we know the volume that needed to rotate the alternator. So this permanent magnet alternator that I use is made from rare earth material, which is very efficient. You can see the power curve. In order to generate 500 watt, I need about 150 RPM. Yeah, and I'm going to explain a little bit more about torque gear ratio and buoy volume. We know that the gear ratio has a relationship with torque, and these are the four proposed designs that I've made. And according to my calculation, the torque increases together with the gear ratio. The gear ratio, the high gear ratio, will make sure that alternators rotate quick enough to produce enough of electricity, but it will result in high torque, which